Okay, so it's time to start. I did send out an email. I'm going to change the homework schedule a little bit. The homework that was due today is not going to be due until Monday. I have a few things I want to talk about today to help you understand about superposition and the canard uncertainty principle. And hopefully we'll have some time at the end that I can discuss the homework assignment. It's all in the text, just need to be walk through it carefully. But in any case, hopefully at the end of today, toward the end of the class, I can help prepare you for the homework if it's difficult for you. Maybe it wasn't. Anyway, it's due Monday, not today. I'm going to be sending out a different schedule of assignments, just slightly different, but it's coming out. So, but just so you know, the homework for Monday is what was originally assigned today, beginning of chapter 3. Okay, so I wanted to discuss, and this really belongs in chapter 1. And I'm realizing that this would have been helpful to have in chapter 1 when we were talking about wave interference and superposition. So we have here a demonstration of wave interference in superposition. And so there's a little thin, there's a plate here with some water on top. Half an inch of water on top here, and then there's a flashlight going through the clear glass. Flashlight goes through. There's a mirror here, and then you can see here what I can see on top. So I'm going to turn on. There's a little just a metal probe. It's just going to vibrate up and down. I have to hold it. So you can imagine what it's doing, right? You can see it pretty clearly, but if you're up here, you can just see that this little probe is touching the surface of the water. And you can see the water waves coming out. What you're seeing is the shadow of the waves, right? Reflected. The light's coming through, and you just see the shadow projected onto the screen, right? Is that clear enough? Okay, now I'm going to take two of them. That's superposition at work. We'll talk more about superposition. Now, you do the two wave patterns, one from each finger, operating the water. Not unfamiliar to you, but I'm just trying to examine this a little bit more. Okay, got that much? Got the idea? Okay. So let's go back to the case where we had just one finger vibrating. You can see the waves on the surface of the water. So what is a wave?
Propagation of energy.
Yeah, sort of. Yeah.
In water,
No, that's not that's water. We're talking about water, not flying on water. It's a disturbance. It's a coordinated motion of the parts of the water. Is the wave a substance? You can see the shadow of the wave here. But it's not a substance. What is it then? Is it a substance or a property?
property,
Property of what?
water.
Water in this case. Right? So how is it that the water can move like that? This is a rhetorical question that I'm going to discuss here. How is it that water can move that way? So it's obviously a coordinated motion of the parts of the water. A very specific way. So let's look at a part of the water. Let's just imagine we have some little bit of water. So here's the bottom. Here's water, thin layer of water. Somehow the parts, so the thing is oscillating up and down, it's displacing the water in and out. And so there must be some kind of motion, but is the water moving this way when the wave is moving that way? What are the parts of the water doing? Yeah, the parts of the water are moving in little circles. Look, circular motion. If I put a bug on here, the bug's not, it's not going to move with the wave. The wave's going to move under the bug. The bug's going to go up and down. If I put a little dye here in the water, the dye diffuses out, but before it diffuses out, it's just going to show you that the water is not moving with the wave. The wave goes from one part to the next. So how does that happen? So there's some part of the water here, and it has neighboring parts, and that part can move from one place to another, and so it can also have impetus, right? Those parts individually, we speak of virtual impetus when they're parts of a whole like this, but the parts themselves can have something like impetus, and they can have a place. Parts are extended physically, they have extension, quantity. Parts outside of each other. So there's another part right here. Those parts can push on each other. So we have something like place. First, the parts are extended. Extension is crucial to all of this. And those extended parts virtually have place, and impetus, mass. They can push and pull on each other. So there's force between the parts. So one part can affect the neighboring part. That's how the propagation occurs. Right? Now, this is specific to water. It's important to understand we're looking at the mechanism, the means by which water supports waves on the surface. Okay. So now in the case of two waves, we have two of them going. Oh, you unplugged me. I never know where this is going exactly. I got some notes here. Thank you. Okay. Now, isn't it interesting that the waves created by one finger and the waves created by the other finger are coexistent? You can see that the two different waves are present at the same time in the same place. That's the superposition. How does it do that? It's not obvious. It's not obvious that one water wave coming this way and another water wave coming this way are just going to superimpose. It's not really two waves. Right? The water at each, if we have a wave traveling, one wave is traveling this way, and another wave is traveling this way. What's going to happen? Well, interesting thing, the height, the place, and the impetus, and all of these things seem to just add, like we're adding numbers, adding quantity, the way it's further extension. So if this one wave coming over here has a peak, and this other wave has a peak at the same place, they're going to be adding together. You get a constructive interference. Whereas if this one coming this way has a trough, the same place as a peak here, it's going to cancel out. So it looks like there's two waves, and there are in that way, but it's one substance, and the part, the water has one height, even though there's two waves propagating through. That's the superposition. So I'm going to give you some more examples about this. Okay, so let's see. I want to go down here. Can't read with this thing on. Oh, I want to show you this. Okay. So let's suppose that there are two waves. And we treat it in the mathematics, we treat it this way. And we have the cosine of two parts. Cosine K1x, cosine K2x, two different wave numbers. Each one has associated with it a wavelength, right? The wavelength of this part is 2 pi over K1. The wavelength of this part is 2 pi over K2. So K1 and K2 are different. Let's see what it results in. We have the 2 cosines. So that's the green and the red. Can you see that all right? And they're differing. The K is different by 5%. I just chose 5% difference. So the green one makes, I think it's 20 oscillations over an interval of 20. And this one makes an oscillation, I think 21. Slightly different. So they start off in sync, but as we go across here, we see this peak is matched to this peak. We get over here and we see the trough is matched to the peak. So when I add them together, I get this, that blue curve, one right here in the middle. You see how that goes? Where the troughs are lined up, the red and the green are in sync, you'll get a higher peak. When they're out of sync, which they have to because they have different wavelengths, then you get this interference. And this is the square. This is the full. So this is F is sum of these two. Then I square it, and it looks like this. Okay. Now let's see mathematically how that happens. I can use the properties of the trig functions. So let's define a big K is the average of the 2 wave numbers, and a little k is the difference. The difference is important. It's what's going to lead to this phenomenon right here that you see. So then K1 is going to be big K plus little k. And K2 is big K minus little k. Right? So there's an average and then a difference. So I'm going to rewrite this in terms of big K and little k. Big Kx plus little k. Kx minus little k. Okay, so far? And now I'm going to use the trig relation, cosine of the sum and cosine of the difference. So the cosine of the sum is cos kx times cos little kx minus sine big kx on little k. That's this first one. And then I add to it the expansion of difference. These terms cancel. So I can rewrite this in terms of that. So we took a sum and changed it into a product. This is an ordinary cosine piece. This is an ordinary cosine piece. But now we have the product, but it's the sum. So big K here, there's a wavelength associated with big K. And there's a wavelength associated with little k. We have the product of those 2 functions. So this function, because k is the average, has a short distance, short wavelength. That's this piece. And then we're going to multiply it by this piece, which has a long wavelength. I'm going to take the product of these 2. And you can see that here. See how we have the short wavelength right here, which comes from the sum, the average. And then we have the long wavelength, this envelope. That's the long wavelength, which comes from the difference. Do you see how that works? Now this is descriptive, not explanatory. The explanation requires us to understand how the parts move in the water. See what I mean? This is purely descriptive. And I can use this to describe lots of waves in different media. Talk about water waves, sound waves, light waves, even Schrodinger wave function. Although we got to come back to that. But this is descriptive. The same mathematical description applies even though we're going to consider different physical systems. So the explanation is different. This is not an explanation of superposition. To understand the superposition in the water, you got to understand how it is these parts can support waves coming from different directions. And that the result is a single wave which has this complicated shape to it, like this. So it all comes down to understanding how the parts move, have impetus, and push and pull on each other. They do it in such a way that you can produce the sum and difference. Just like when I have the two, both of them going, I see two waves superimposed. Not obvious. Very interesting, actually. You think about it. And the way that I'm trying to get you to think about it is in terms of the physics of the medium. In this case, water. Allows superposition of waves. Not only does it support waves, but it allows them to superimpose, to be superimposed. Okay. All right, so you hear me, right? I'm producing sound. And the sound, how does the sound travel? How is it? All right, so first, yeah, there's some kind of motion of the parts. What is the sound a substance? No, it's a property of what? The air. To the extent that air is a single substance. You could have, this is a lot like sound wave, that we could have sound under the water, not just on top. You've heard sound underwater, right? Okay. Then we could have two people talking. So count to 10. 1, 10, 9, 8, 7, 6, 5, 4. Am I messing you up? You can hear us both at the same time. In fact, if we keep talking, you can even change your focus mentally. Pick out one over the other, but you're hearing them both. The sound that you're hearing is a superposition of both. That sound wave's coming from over there, sound wave's coming from here. You can hear them both. They're present in the air. Sound superimposes. How do we understand that? Explain that. We have to understand how the air moving around, some part of the air here has a place and an impetus, and it can push on its neighbor and push and pull on neighboring things. And this is done in terms of pressure in the air. Okay, it's interesting. That has superposition just like this does. Different physical reason, different explanation, different cause and effect. Somewhat similar because we're talking about place and impetus and force. But not the same exactly, a little bit different. Same mathematical description. Different physical things going on in those two cases. Okay, how about light? We had a laser in here back at the beginning of the semester. And we had the laser was taking different paths to get to the same point on the screen, going through two different slits, for example. So the same light was interfering with itself by going through the different paths, taking the light through two different paths. We had the double slit experiment. We had light coming in, and we had this resulting pattern here, which showed up as a difference in the distance that this one traveled and this one traveled. So they had different distances. So we could get a constructive or destructive interference. Depending on the path difference between these two, there's one wavelength involved here, but there's two different distances involved. So that would set up a constructive and destructive interference on the screen. Okay, so how is this working with light? Now we're talking, is light a substance? It's property of what? Right. We can have two waves present at the same time. If they were substances, we couldn't have it present at the same time. The water waves are not two different substances. It's a property, a combined property of two waves, but it's a property of the medium. In the same way, you're seeing light from all kinds of different sources. From outside, from the light bulbs, from the screen. And so the light is not a substance, it's a property because these waves can exist together in the same medium at the same time. So the medium is the substance. Okay. But how is it that light can propagate from one part of the planet to the next? Again, we have the same characteristics. The parts of the planet are extended. Each part has a kind of a left side and a right side, the top and a bottom, front and back. And it has neighboring parts. But now we're not talking about the motion of the planet, or we're talking about propagation of an electromagnetic wave. What is it that we're talking about? What is propagating in the planet? Light, yeah, and what do we understand light to be?
Isn't one part activates the next?
But what is being activated?
There's a quality of the planet.
The quality of the planet, specifically what?
Light.
Well, not light, but say
A field.
A field, or E field or B field. How do you? Well, so the A field is the most fundamental way of looking at it. There's a quality of this part of the planet, and also there's a changing of this. So there's a dot. How is the quality changing in the planet at this place? This is analogous to something like a position and something like an impetus, but it's not impetus, it's not position, it's changing. It's not a wave in this fashion of parts moving. That was the old idea of the ether, that parts were somehow moving. And that doesn't work, that's not correct. But you still have parts. And what's happening here can influence the neighbor. And one part can influence the neighboring parts. And that's how this thing can propagate. The electromagnetic field can propagate because one part affects the next part. And so it can pass the quality, in a sense, from one part to the next. And that will support the superposition. We can have a light wave traveling this way, a light wave traveling that way. There's only one A field in this part of the planet. There's not two A fields. There's only one. But we can understand it in a sense as that mathematical superposition. It's like we wrote the cosine K1x plus cosine K2x. We can think of the A field as being a superposition of two different waves propagating through. It's interesting that it can do that. Right? So the math is descriptive. But now you're starting to talk about the physics of this process. How is it that the superposition can occur? And it happens in water, it happens in air, it happens in the planet. You see, it's not obvious. So I could write down, some people, if you just look up superposition on the internet, you'll get this. And they'll work it out just like I did. That's the description, it's not the explanation. You see the difference? Okay. All right, here's another. We can take this one away. Michael, did you grab that? Mr. Michael, did you grab that? Yeah, I'm gonna. No, let me be the other. I'm gonna grab the other end. Just grab that. Stand over by the door here. We're gonna stretch it. See if we can hold it horizontal. That's not too good. It wants, for some reason, wants. Okay, hold it for. Oh, I'm sorry. No, the other way. I want to twist it. There we go. All right, you see how this thing works? It's a torsion. series of pendula hooked by torsion. What's exerting the force? So if I turn this one, the neighbor's turn. Why? You're connected through the piece of metal here that's twisted. When I twist the metal, it's going to put a twist on the neighbor and so forth. So it's propagating from one part to the next. Each part is extended and it's connected to its neighbors. Again, this is another wave thing. I can do a wave. Watch the wave propagate back and forth. Right? Okay, if we had more time to practice, I would get one going and he would get one going. Actually, you can see it bounce off the end, right? So there's a reflection. That's interesting. Waves bounce off the edge, the end. Now let me try to do it. So if I were with a little more practice, the idea would be I'd get a wave going, and then I try to hit it with another one coming back, right? Show you the superposition. Isn't that interesting? So somehow this torsion here doesn't get confused. The fact that there's waves coming from different directions, it just transmits from one neighbor to the next as though the two waves existed independently. But they don't. There's only one displacement at each point, only one torsion, one twist with each pendulum. You see how you get a wave traveling and then pass through another wave. Thank you. Okay, I'm going to show you a better one. Dr. Sardashti sent this to me. Sound is, I'm going to turn this light down here so you can see it better. Okay, the sound is not important. I'm hoping you can see it. It's a little bit dark, but I'm hoping you can see it. He has two of these torsion pendula, torsion chains. One here and one here, and they're a little bit different from each other. It's not important that they're two. I just wanted you to note that he has them. Don't worry about the sound. I'm going to find a place in here where he's going to show it to you. This is Bell Labs from 1950 something. Okay, there you go. So he's gonna. That's a nice torque, and he's got a slow motion camera that helps. Okay, they bounce off the ends. They come back together. That's superposition there. The waves just pass right. It looks like they're almost passing through each other. But notice at each point there, okay, the waves travel apart, they bounce off the end, come back together. And it's like they pass through each other. But at each point here, each of the pendulum has two things, as a displacement and a speed, a velocity, in the vertical direction. Those two things are connected to the neighbors. They exert forces on the neighbors. Each pendulum exerts a force on the neighbor. Okay, now he's going to change it here. Okay, so the reflection off the end depends on how the end is held. In this case, the ends, the one that you just saw, the ends are free. And let's see, in that case, with the free end, yeah, with the free end, you saw the wave bounce off the end and it comes back the same sign. Upward wave propagates outward, comes back, and they're both still up. If you change the end condition, you make it clamp it so that the pendulum on the end can't move. The reflected wave comes back negative. You have an up wave hitting the end, it reflects, comes back down. So he's changing the end condition on one end. See, he's clamping it there. Now he's going to do the same thing. Just only going to do that to one end. No, do it. Oh, no. Leaving it free on one end. Oh, he's showing you how the wave. That's clean. He's showing you standing. You have a left wave and a right wave coming together to produce the standing. I saw that. Let's see. Part here. wasn't. Come on. Let's see. Oh, no. See, he's making analogies to electrical analogies, right? There are waves in circuits. There are waves. Charge is moving. So there's an analog. I was looking for the place where I had it. So these two waves are both up. If you have an up wave and a down wave coming together, there's an instant where the whole thing is flat. They cancel out. But it's not like they cancel out completely because then the waves pass through each other. So, and that's because at that instant, when they come together, you have an up wave and a down wave. This one's going this way, down wave going this way. When they meet, the whole thing is flat for an instant. But the parts are still moving, they still have impedance. And so there's still some motion going on. And then this will, let's see the other way around, I guess. Still have impedance. And so now this wave is going to pass through this way. That's because they, even though it's flat for that instant, they all have impetus. It's going to keep it moving. The waves will pass, look like they pass through each other. Wish I had that part. Pretty neat. Okay. Okay, so now here's the part I'll show you here.
Random question.
Yeah, hold on a second though. I'm on a roll here. Hold on. I'll get to your question, but I want to show you something. Now we're getting to the canard uncertainty principle. Okay, so I have now more than one K vector, more than one wave number. Let's suppose I have 2, 3, 4, 5 different values of K. So I have not just 2 cosines, but 5 or 6 or 7. I add them together. Okay, so, and I'm going to play this with sound. I'm going to do this with the sound generator. So I'm going to start with one sound. Just one K, one wavelength. This is a pure mode. I told you it has a characteristic sound. Hear that? Kind of a bare sound to it, right? It's not a very rich. Can you hear it okay? Okay, that's just one wave number. That's just cosine. Turned into a sound wave. That's one frequency. Okay, well, let's suppose we have 2. All right, we did that one. You saw that one. I'm going to put 2 together. Okay, you see the superposition there, right? Okay, there's a lot of oscillations like this. There's an envelope. So there's a sum and difference frequency here, an average and a difference. These tiny oscillations, that's the average, and then the envelope is the difference between the 2 frequencies. Okay, listen to it. Goes away. Big and it goes away. It's the superposition of the 2. All right, let's suppose we have more of these. I've got now 8 different modes added together. Oh no, here they are, 5 modes. You can see here's the probability distribution. It's like a probability distribution in K. I have 5 modes. That's the yellow stuff there. I have 5 delta functions. And add them together. Okay, so now what I accomplished though was I could scrunch. I have most of it scrunched into 2 intervals here in this plot, but it's mostly scrunched into here. And then it's quieter out here. What if I get more? I'm going to do more modes. Okay, now there are like 10 modes added together. 10 different wave numbers, all pretty close together, but some spread. There's a standard deviation to the probability distribution. You see the width is now expanded in K. Delta K is bigger now. Or in terms of frequency, the frequency spread is bigger. And look what happens here. It's more localized. So I have a little bit of raining, a little bit of beating in between. And I have a big peak, but it's tight. The more components that you add here, the tighter the sound becomes. See how it's tight there? Now there's a little bit of ringing on top. That's because I have discrete wave numbers rather than having a continuous distribution. But you can see the idea here. The wider the spread in K, the shorter the spread in X. That's the Canard uncertainty principle. I'll say that again. To get the uncertainty in X, we were doing sigma X, sigma K greater than or equal to 1/2. I took out the H bar instead of using P, I have K. K is a spatial frequency. So if I want to make X small, I have to get a bigger sigma K. If I want to have this occur in a narrower range, I have to have a bigger spread in K. Does that make sense? It's a superposition of many different Ks, lots of them. In fact, if I have a Gaussian spread, then I'll produce a Gaussian here. And that was the example you did in your homework. Show that the sigma for a Gaussian in X, take the Fourier transform, then you get a sigma for a Gaussian in K. And the product of those two was actually equal to 1/2. So if I decrease this, I localize it in X, I have to have a spread, bigger spread, wave numbers. See how it works? All right, so there are lots of questions. Let's go back.
What happens if you have two fixed ends? Does it behave the same as two
Oh,
free
the-
ends?
Yeah, so if you have you're going back to the torsion spring,
And you just kind of smack it in the middle, two fixed ends?
right? If this is traveling over here to a fixed end, when it reflects off, it'll be negative coming back, and so will on this end, it's also fixed. Then it comes back reflected negative like that. The one I was trying to find was where you had a free end, an open end, where the reflected wave comes back positive, and then we had a negative reflection off the fixed end. And there's an instant when they meet back in the center where the thing is just flat. You just take a picture of it at that instant, it looks like nothing's happened. But they pass through each other. This wave will continue, this wave will continue. But the only way it can happen is because the parts have influence. Just the right way. But now it will continue the wave motion on the other side. Just rough.
I was gonna say, so if you do the sum of a lot of your nodes and their K, like the difference in the K values, like if they're like not close to like the average, for example, the spread is like really big. Can I see that? What is this the K's that are like they're the
Yeah.
same?
These that yellow is not showing up real good with the gold. I can keep spreading it out more and more. Or I could increase the spacing between them. Maybe that's what you want.
Yes, sir.
Okay. But the principle is going to be the same.
Yeah.
I'm trying to get them all to be pretty close to the average, but changing the number to get the spread, okay, rather than moving them out. Okay. The point is that you need lots of wave numbers, not just two wave numbers separated. You need lots of wave numbers together to get this kind of localization. And that's the important point. Our uncertainty principle. Okay, one more thing. So we looked at water, we looked at sound, we looked at light. All have this wave phenomenon, well, let's say fauna, right? Water, air, fauna. All have qualities that support this kind of wave motion because they're parts that are extended that influence the neighbors. So they can pass along the influence from one part to the next. And you have this allows superposition to occur. You can have waves traveling in opposite directions, for example, that just pass through each other. Okay. What about that? What were we looking at in the water wave? It was the height of the water. Sound wave is pressure of the air at each location. With light, we're talking about the A field, or the E field, D field, they're all related to each other. And the fauna. What's that? You know what it is. It's not a measure of a particular quality of fauna. Right? It's not that. So it's not like those other cases we were just looking at. There's the height of the water wave. There's the pressure of the sound wave. There's the A field and the light wave. This is a wave of a kind, but this is not a measure of some quality of the fauna. That's the way this is going to get difficult, because this is not itself a measure of some quality. This thing is a encoded information encoded into this function that gives you information about the probability how the electron is moving under the influence of the guiding wave. So behind this, there is a wave, but this is not the measure of the amplitude of the guiding wave. This shows the influence of the guiding wave on the electron, and it's all buried behind the Schrodinger equation. Somehow, it's not made explicit, the guiding wave, the presence of the guiding wave. So it's the combination of the particle and the wave that's encoded into this thing. Nonetheless, we have a wave equation which has a superposition. How does that work? We don't really understand that very well. But it's analogical to the other ways that we looked at, where there really is a quality of some substance that we're looking at. This is not like that, but we still have superposition. And we also do have, evidently, superposition of guiding wave. Guiding wave can superimpose. When we did the particle in a box, we looked at a wave function, which was a superposition of the lowest ground state and the first excited state. What does that mean? That means that there is some kind of resonating structure of the guiding wave. Guiding wave is built up in some kind of superposition. So there is a kind of corresponding to this superposition mathematically. The explanation is that there is some kind of structure of the guiding wave that has been brought into some kind of superposition that corresponds to this. This is not explicitly the guiding wave itself. Right? So there's a kind of extension here. We're taking things that we have an understanding of, and we're using it kind of analogically to develop the Schrodinger equation, which is a wave equation. Psi itself does not measure quality of the quantum. So it gets a little harder to understand what's going on and why superposition should work in quantum mechanics. You can understand it better for water and sound and light. This is going to not have that kind of underlying explanation, because buried behind this are details we don't know. Does that make sense? Okay. Mr. Rupp.
So it's just looking at the net effect of all the net effect of all that qualities that.
Okay. Rather than trying to put it into your own words, go back to the inside front cover. right? The wave function is a solution of the Schrodinger, let's see. The guiding wave structure is associated with different powers of the fauna. The effect of this structure is described statistically by the wave function. So it's a statistical description. It's more descriptive than explanatory. It's a statistical description of the combination of the particle with the guiding wave. Without the detail, it's statistical, right? So that's what we mean by statistical. We're not delving into the details of the individual parts of the guiding wave and particle. The combined effect is described statistically by the wave function. Does that make sense? So I'm going to put some of this in the chapter 1 when I teach this next year. I'm going to put the wave interference and superposition back in chapter 1. Because it's good for you to see that and realize that the descriptive part of the math needs to be supplemented with an explanation in each of the cases: the water, the air, lights, the fauna. This is helping for you to understand better the physical content of the canard uncertainty principle by superimposing lots of different waves together. Does that make some more sense? Okay, good. So there's not much time here. I didn't really, but I think if you read the text carefully, you'll be able to do all the questions in the homework. If you have problems, drop me an email. I'll help you along. Okay. Have a good weekend.